welcome. This is lecture number 13. In this lecture, we are going to talk about converters, objective and control implication using MATLAB models. So, in this lecture, we are going to first talk about the understanding behavior of a practical voltage source while driving a switch mode power converter. Then we want to also demonstrate, because already in the previous few presentations sessions, we have discussed about the development of MATLAB model. So, in this lecture I am also going to talk about the models are scalable, because we talked about that we created one subsystem for a converter, and I will show you that if you develop the subsystem of a filter or a source, you can simply plug and play, attach that block to the another converter and so on. So, that also with a practical source we want to develop a scalable MATLAB model. Then we want to understand what are the converter objectives and control implications. So, before that we want to create few motivating MATLAB test cases to show why do you need like a various static, dynamic and other objectives, and then what is the need for control. Then we also will talk about some power stage design guideline and few power stage designer tools. And finally, the MATLAB case study will be, in this lecture we will also show MATLAB case study to understand the control requirement. So, first we will talk about a voltage source. When we talk about voltage source, the first thing that comes to our mind is an ideal voltage source, and here I am talking about an ideal voltage source. So, this is an ideal voltage source, So, in this source we have connected a load. So, this load can be resistive load, this load can be constant current load. So, it can be different type of load, but the objective in this particular talk, what I am going to talk about, what is the current and voltage characteristic of a ideal voltage source. And in various textbook from our undergraduate we have studied that if you draw current, but yes, generally we do not talk about the limit of the current, but suppose if the source current has certain limit, within the limit, if we draw within the limit, or in fact the ideal definition is there is no limit on the current. So, if you draw current from the source, any amount of current, the voltage should remain constant. That is the basic definition of an ideal voltage source, and it is shown here. So, that means your current you are drawing current, but the voltage remains constant. You can see this is a constant voltage. That means the voltage remains constant irrespective of current magnitude. That means there are two ways of looking into this problem. The one way, suppose we take a resistive load, suppose we are talking about a voltage source, and we are, let us say, we have connected a resistance. Okay, this is a variable resistance and this is a source. Now, but we have to keep in mind, because if we vary the resistance, suppose we decrease the resistance, let us say we start with the voltage source is of 10 volt and we start with a resistance of, let us say, 100 ohm. Now, we slowly decrease the resistance value. So, if you decrease the resistance value, naturally what is the current flowing through this resistance? The current will be simply Vs by R. That means, if we reduce the value of the resistance, the current will increase. But we need to keep in mind that this resistance power rating should be such that it can withstand that heat generated, because I square R loss that will introduce, that will actually lead to heating effect, because the Joule's law, it comes from the Joule's law. So, that means if you keep on decreasing the resistance slowly by using a potentiometer, then the current will increase and you can actually create this condition, and you will see the voltage should remain constant if it is an ideal voltage source. But when we are talking about slowly varying resistance, in fact manually varying, then it relates to the very slow characteristic, and that is nothing but the DC output impedance. That means we are talking about the output impedance of this source is 0, there is no output impedance, that means there is 0 output impedance, there is no drop. Now, we can also talk about suppose we create a transient case study, that means another case study where suppose this is my voltage source, again it is a 10 volt. Suppose I apply a switch and this is my constant current and it can be resistive load. This is my I0 and this is my source current. So, if I turn on and off this switch S, this is my switch S periodically, that means when you turn on the switch suddenly, and let us say this I0 is, let us say we are drawing some maybe 10 ampere current, maybe let us say we are drawing 10 ampere current, 10 ampere. So, when you connect the switch suddenly we draw 10 ampere, when you disconnect the switch then we are totally disconnecting, that means the source is now unloaded, that means there is no load, and when you connect it is fully loaded, that is 10 ampere. So, this is another current of profile where we will talk about the transient current. Okay. So, earlier the current was continuously changing, but it was a very slow process. So, we are talking about the DC output impedance. Here we are talking about the current is repeatedly connected and disconnected, or you can create a pulsating current by means of a current source. But remember, this slew rate of this current has to be much faster. This relates to the AC output impedance. So, if there is no change in the output source voltage even after applying the transient current, then that means then we talk about two things. The one thing is a zero output impedance, that is the DC characteristic, and the second one is the infinite bandwidth, that means it has no undershoot overshoot in the voltage irrespective of the transient current. Okay. So, the ideal voltage source has two characteristics. In the DC characteristic we talk about zero output impedance, and the AC characteristic we talk about infinite bandwidth. That means there is no frequency dependent term, it will respond to any transient current. But we know that ideal voltage source does not exist in reality. So, all voltage sources are practical, and when we start our undergraduate first year or second year, the first thing we are taught that if we want to convert an ideal voltage source into a practical voltage source, the first thing we do, we add a series resistance. So, this is the series resistance we add. This resistance is a part of the source because it is the internal resistance of the source, and as it this is a now ideal, this is ideal voltage source, and this is our internal resistance we can talk about. This is our internal resistance, our internal resistance, of the voltage source, it is a part of this. That means what is accessible to us is this two terminal, terminal 1 and terminal 2, these two are the accessible part. So, this is our source voltage, actual source voltage, that means this is our V of S. In this case, if we draw the current and voltage characteristic of the ideal voltage source, the practical voltage source, what we will find, in fact, if we take a battery, suppose you for example, you take a battery, okay, and battery positive and negative terminal, and if you connect, I mean this you can try it out, you connect a variable resistance like a pot, this is a battery, and you decrease the value of the resistance, you will find the battery voltage is decreasing, it is like something like this. That means, when the battery voltage is decreasing, when you are trying to increase current, that means you are drawing more current from the battery, this is the source current, now here battery is the voltage source. Then the voltage is slowly decreasing, and this can be model or this can be characterized by adding this resistance, and that is why in the ideal source there will be a series resistance here, that is our RD, okay, as if this is an ideal voltage source. But this captured the load regulation aspect, that means all voltage source has some finite DC output impedance, the DC characteristics, but it does not capture the transient, because still if we apply a transient current, suppose you again take a battery and again we take a battery and now we apply a switch, and again we apply a resistance here. Now we turn on and off this switch in a periodic manner. Now you will no longer find that it only, so there will be some effect of the battery. That means battery voltage, if you draw, we will soon see that battery voltage was clean. When you start drawing current, there will be some kind of effect will be there. Again you leave like this. So we will see some transient effect, but this only adding resistance is not enough to capture this behavior, because all voltage source, practical voltage source, has finite output impedance as well as it has finite bandwidth. Okay? But this model still capture what we learned, the basic practical voltage source. That model does not capture the bandwidth effect, but as if it assume that it has an infinite bandwidth. Now we want to add frequency dependent term. So we want to model a more realistic voltage source, and this can be modeled by introducing some effect of LC circuit. And because this is, even if you consider a DC-DC converter, which is the major theme of this course, almost the whole course is based on the control of DC-DC converter. The DC-DC converter itself, we want to regulate the output voltage. That means we want to achieve a regulated output voltage, which means we want to achieve a voltage source. That also we will see that the DC-DC converter, we generally connect a output filter. So that filter will have some finite output impedance as well as finite bandwidth. So that means there will be some overshoot, undershoot. And if you take a step down DC-DC converter, buck converter, we know that this L inductor is there in the output side and capacitor is there in the output side. So from applying that common sense, we can think of an ideal voltage source can have some amount of finite inductive and capacitive effect. But you may model in more accurate way, but this is one of the simplest way to model, which can capture the transient behavior or the finite bandwidth aspect of a voltage source. That means this is what we are going to. Now this voltage source, if we do AC model, that means if we now, it is an ideal voltage source, and this, if you look at the impedance from this side, that means we are talking about the output impedance of the source, of the voltage source. Then here we are talking about the AC characteristic. That means there will be a frequency dependent term, and that will lead to some overshoot, undershoot when we consider pulsating current, that means this transient current. Okay? And it will also it will also capture the DC characteristic, that we will see, because if you talk about, because in the previous consideration we only took a resistance here, this resistance we have considered, that was a DC. But now in this AC characteristic, if you want to analyze DC, that means you are applying your constantly, suppose this is a resistive load, okay, and you are slowly changing the resistance value slowly, then that means it is a low frequency effect, and in the low frequency, inductor will behave like a short circuit and capacitor will behave a open circuit. And if it does, then this resistance, this will be equivalent to again this voltage source V in RD, and then here we are connecting, this is my load. So this is my source terminal, that means this is my actual voltage source terminal. So this is a low frequency model of this, that means this is a low frequency model of this, where we are assuming that current is changing very slowly, where this transient effect will not come into picture, because it will be died out, it will decay out. Okay? Except for the fact that if this LC oscillation may cause some oscillatory problem, if you take for a specific choice of LC, for some set of LC, you may end up with some oscillatory behavior, but we are not talking about that. Okay? So output impedance, transient behavior. In order to get the output impedance of these characteristics of this source, we need to get the AC equivalent circuit, and that can be obtained by considering all DC term, because we will learn in the subsequent lecture from equivalent circuit model, that from a given circuit we can extract the DC equivalent circuit, we can extract AC equivalent circuit, and also the original model is a large signal model which consider both DC and AC. And in order to extract AC equivalent circuit, we generally keep all the DC quantities 0. So, for a voltage source, ideal voltage source should be short circuited and ideal current source should be open circuited, because current we want to replace 0. And then we can get the AC equivalent model of output impedance of the source like a parallel branch of LC circuit with parasitic resistance. Then we can write the output impedance of the source, and it can be shown that from this model the parameters are this. In fact, this is quite similar to the output impedance of a buck converter, only the value will be different, the different values. Now, if you consider this model and if you make that S equal to j omega, that means the frequency response, and if you substitute omega tends to 0, that means at low frequency behavior, all this term will become 1 unity and it will become RD. That means this is the DC, that means this is the output impedance at 0 frequency. That means it is the DC output impedance, and that we have started with the practical voltage source by putting an internal resistance in series. Now, we want to incorporate this, okay, because what we talked so far of a DC-DC converter, we have considered an ideal voltage source by just taking a number in the MATLAB. But in reality, the voltage source will be practical, and in this course we want to understand the control objective. So, we need to know if the converter is connected to a practical voltage source, then what causes that can happen, and then in the control as well as the other aspect in the converter design aspect, how can we take care of such a practical aspect. So, in order to get, we need to develop the MATLAB model of the source, and we have already discussed in lecture number 4 how to build the model which can be used for simulation, and this is a similar approach. That is why I am not going detail again and again. Here you can set the initial value of this filter current which is passing through this inductor, okay. And again you can write the voltage across inductor is the differential equation, and from this equation you can get this model. That means you can realize this equation using this model. Similarly, you can realize this dynamics of this capacitor, because this is a capacitor current, the capacitor current going through this path, and then the terminal voltage of this filter, which is nothing but the source voltage, can be obtained by adding this together. That means here we got VCF. So, if we add this VCF plus, if you tap this point and if we add this RF2 and if you add together, then you will get actually V terminal, which is a source voltage. Okay. This is a complete model of this particular filter, and this we can build in MATLAB, and I will show you just in a few minutes. So, we have this model with us, and this model you can make a subsystem, and in that subsystem if you look at this, for this source, that means this is the impedance model of the source, right. This is the impedance model of the source. For this impedance model, this is the ideal voltage source. I mean, this is an ideal voltage source which is here, ideal voltage source, that is the input to this block. Another input which the current going out of this block, because they are depending upon that how much current the other circuit, because we need to connect this source to a load, and the load can be in this case is a DC-DC converter. So, this DC converter will draw some current. So, that current is the load to this block, input to this block, this simulating block, depending upon how much current it is drawing, whether, because we told that earlier, if we connect a pulsating load to the source. So, that means depending upon the nature of the load, the amount of current it is drawing, the source voltage characteristic will vary. That means the time domain waveform of the source voltage depends on the profile of the current that you are drawing out of this source. So, that is the input. Then what is the output? The output to this block is the terminal voltage, which will be connected to the input to the next block where we are going to drive, which we are going to drive. We can also optional, it is optional that we can tap this current, we can check, though in actual circuit this block is a capacitor. So, it is a ESR of the capacitor, which is an integral part of the capacitor. So, we cannot access it, but for simulation we can check it. We can also access this current of this inductor, but again these are optional, because whenever we talk about a practical voltage source, I will say a practical voltage source. So, only this terminal voltage is accessible to us, nothing else is accessible. And what is accessible is the current going out of this terminal, that means this current, which is the input. And here for our understanding we created this model, but when you actually take a source, let us say if we take a power supply of a lab, that means we generally use power supply for connecting as the input to the DC-DC converter. So, now this power supply can be treated as a practical voltage source, in which we can only access the current coming out of the power supply and the voltage, terminal voltage of the power supply. Okay. So, that means this is accessible, this is something accessible, and this is accessible which is coming out. The other things are internal, but in this simulation, since we are connecting, this is a separate, so we are connecting an ideal voltage source. So, this whole thing is combined as a voltage source. Now, I want to show the performance of a practical voltage source. So, I have created a model, I will go to the model, it is a Simulink block. Okay. If I go inside the Simulink block, it has two subsystems. One is the inductor current dynamics, and which we have discussed in the converter model. So, I am not going to do that, but I will show you in the Simulink block. The another dynamical equation is linked with the capacitor current of the filter. Okay. And then these two are the terminal. So, these are the terminal volt of this block, and we have taken for simulation the LF, that means the inductor of the series path is 0.202 microhenry, that is it is 20 nanohenry, because this could be trace inductance, as if we are putting even it can include the cable resistance, inductor of the cable resistance, because we generally connect cable from actual power supply to the DC-DC converter. So, that inductance can be you can incorporate that, or you can put a large value, does not matter, but I want to show you. Then the capacitor, which is in the output side of the source, and this is the DCR of this inductor, and this is the ESR of this capacitor. Now, I want to show a simulation case study, because that we have started with the very beginning, that if we draw a pulsating current from the source, how does the waveform, the source voltage look like. Okay. So, what I am going to show, I want to consider a pulsating load current profile. That means periodically I am connecting and disconnecting this switch, so that I am taking as a 10 ampere current, and this I take as a 12 volt source. Okay. And then I am applying periodically, that means this switch I am turning on and off in a periodic fashion. Okay. So, this is the simulation case study. See here the red trace that is shown here, red trace is nothing but I out, that means this is because this is nothing but the constant current source, that means this is a constant current load, because we are connecting a load. So, that is why irrespective of the supply voltage, because we are talking about a voltage source. Now, when you talk about a constant current source or load, that means the current load will behave like a exact ideal current load. So, that is what we have emulated here, the red waveform. Then the red waveform here is the ideal voltage source, that is V in here. Okay. But what is accessible to us is that source voltage terminal, and that is indicated by the blue traces. So, this is what is accessible, because as if we take a laboratory power supply, and if we look at the waveform, that means if we look at the waveform of the power supply, our Vs is the power supply, and we want to see what happens. Suppose if we do not draw any current from this, here it will be, but suddenly if you put a transient current, then there will be some overshoot effect, Again, if you remove the current, there will be some undershoot effect. So, this is exactly what is happening here by the blue trace is indicating. That means, there is a transient effect due to the finite bandwidth of the voltage source, and voltage source has some, that means it will respond to the transient current if you apply some step current. Now, why we are interested in this? Because our DC-DC converter, another point I want to show here, you see here initially these 2 points are exactly overlapping because there was no, we are not drawing anything out of the source. That means our both inductor, capacitor, they are all kind of discharged. So, that means this point will be same as the input voltage. But when we are applying a 10 ampere current, there are two things. So, this portion is a transient effect. We can see the transient effect. This is a transient effect, and this portion is the steady state effect. So, in the steady state, you see the blue trace voltage is slightly less than the red. That means, it has a drop, and that drop can be attributed to, suppose if you, what is the RD? We took RD to be, that means this is my DCR. So, it is 2 milliohm. So, 2 milliohm into 10 ampere is how much? Is a 20 millivolt, 20 millivolt. So, if you measure, it will be something around 20 millivolt difference. So, this drop is due to the resistance in the series path, and in DC equivalent circuit we have seen the inductor can be shorted, capacitor can be opened. So, it will look like an whatever practical voltage source we have learned in our very basic undergraduate course, that means the resistance in series that will be reflected. Okay. Now, when such practical source is connected to a buck converter for driving, that means as if this is my source and this is connected to the DC-DC converter. Okay. And the input voltage, for sake of modeling, this is our ideal voltage source, and in most of the simulation in subsequent we may not consider this because we are assuming that, I mean, this effects is negligible, but it may not be negligible. But I want to show that if you draw, because this, if you take the buck converter, the buck converter input current is discontinuous. That means it should create a similar transient effect in the source if you repeatedly turn on and turn off this high side switch, because it will appear like a pulsating load, and this pulsating load will create such transient effect, and this transient effect will actually cause, which is called conducted EMI, because it will cause some disturbance in the power supply, and that is propagated through this current, source current. This is propagated to the source current, and that is replaced, that can be used to quantify the conducted EMI. That means, if you take the power of this voltage source, not all power will be associated, or it will be around the DC value. There will be some power which will appear at the damp frequency of this transient behavior, where some power will come, and that power can come at very high frequency, and that is associated with the EMI effect. And if that power amplitude is large, then that power can interfere with different communication devices. Okay. That means the practical buck converter. Now, if you take a practical voltage source and which is driving a synchronous buck converter, a practical buck converter, you see I have taken this parasitic of the switch, parasitic of the inductor, ESR, though we have not considered the switching capacitance and other, like drain to get to source capacitor, then drain to source capacitance, those can be considered also, but their dynamics are even much faster. Okay. So, now how to build such model like a plug and play? The synchronous buck converter, so far we have shown whatever model we have developed up to lecture number 12, we have not considered the input current in that in our simulating block. But now it is very easy, because out of this model, what is input voltage of this converter is source dependent, because you are connecting a practical source here. Okay. Earlier we use just a number. Now the input current will for the buck converter is same as the inductor current. When the switch is on, that means when your Q equal to 1, it is nothing but the inductor current, and when the switch is off, it is nothing but, that means Q equal to 0, it is simply 0. That means there is no current. Okay. That means input current depends on the inductor current as well as the status of the high side switch. Okay. So, we can create, now we have earlier model, but we have added this extra terminal because this terminal will be used for building block for adding input filter or a voltage source to the converter. Okay. Because earlier we have shown the converter Simulink model where we have connected, this should be 1 by R, a resistive load because the current is equal to V0 by R. Okay. But now, so that means we have connected resistive load. Now we want to connect the filter to the converter. So my question is that should we need to make a whole subsystem again? I want to tell no. How? That means our practical synchronous buck converter model we already have. The only thing I have added is the input current I told you, which is nothing but what? The input current I have developed is Q into IL plus 1 minus Q into 0, because when the switch is off it is 0. So, this block, now the input current of the buck converter is nothing but the output current of the source. So, it is simply connected here, and the output voltage of the source terminal voltage is nothing but the input voltage of the converter. Okay. That means, if we just connect them, it is like a drag and drop model, right. So, as if we have a converter and here we have model another model. That means, if you want to add another module like input filter, you can just connect in between, and it is again drag and drop model. So, this model are plug and play type. You develop one model, but you need to create the terminal such that you can interconnect the source or any other converter. In fact, I will show you in lecture number probably in say 16 where we want to show that another converter, if you want to create a cascaded DC-DC converter, that means the first stage, second by second stage, then one model just you create copy paste of the other model, change the parameter, whole model will remain same, then output of the first converter will be the input to the second, and the input current of the second converter will be the output current of the first. So, the similar configuration can be created to create a plug and play type module. Okay. So, this is the source impedance. Now, we can, this is a complete model. Okay. And with this model, we want to create some simulation parameter. So, I have created this parameter for simulation. For the buck converter, it is the same that we have taken earlier. This is I called as a buck converter parameter, or you can say it is a buck converter, just a minute. So, it is a parameter file, I will show you, it is a parameter file. It is a parameters for the buck converter. Okay. So, this is a model and all the parameters are defined in a separate .m file. Now, I want to show first thing. The first thing is that here we have taken an ideal voltage source and we have created an open loop case study, where our objective is I want to achieve output voltage nominal value to be 1 volt. That means, this is my reference voltage, and my input voltage here I set 12 volt. Okay. So, if you take open loop DC-DC converter, then what we will do, and we will simply set D equal to 1 by 12, because D equal to V out nominal, which is the 1 volt divided by V in, and this is nothing but 1 by 12 that I have taken. Now, interesting point here you will see, I have considered two load resistance value. It is an, again here we have connected an ideal voltage source, because we will see the practical voltage source in the subsequent simulation result. In the ideal voltage source, but the converter is practical, that means it has parasitics and all. You see, when the load resistance was 1 ohm, that means here R equal to 1 ohm, then what is load current? Load current, it will be V0 by R, and V0 is very close to 1. So, load current will be roughly 1 ampere. Now, I have taken two cases, one ideal buck converter, which is the blue one where there is no parasitics, and the red one is the practical buck converter, which is there are parasitic. And you see at 1 ohm resistance both are nearly identical in terms of the average current, in terms of the average output voltage, they are almost close to each other. But when we increase the load resistance from 1 ohm to 0.05 ohm, that means our target load current was 20 ampere, that means we wanted to achieve I0 nominal to be V0 nominal by R, which is nothing but 1 by 0.05 is 20 ampere is my nominal current. But for the ideal case, you see here we are getting 20 ampere load current nominal. But in practical case here it is less than 20 ampere. Another point, the output voltage here you can see it is roughly 1 volt, it is 1 volt average, but here it is much less than 1 volt. Now, the question is why it is happening. That means this difference between this voltage, which was almost negligible for R equal to 1, now becomes very much prominent, and that difference increases when the load current increases or the load resistance decreases. That means this can be attributed to our output DC impedance, DC output impedance, because we just now talked about a DC voltage source. That means if you take an ideal buck converter, you can assume that you have a nominal voltage, that is our desired value, nominal with some resistance RD, and this is my actual output voltage that we are getting, and this RD is 0 for an ideal converter, but in practical converter when you go for DC equivalent circuit, I will show you this RD primarily depends on the inductor DC resistance of the inductor and the on state resistance of the switches. And if you have a diode based implementation, this also comes, this drop can be also part of the diode can contribute to this drop. Okay. So, that means this RD, it shows a practical voltage source where the voltage drops when the load current increases and which is consistent. The another point I want to show, I have just shown you the transient effect, because it is an open loop. So, the voltage is not simply changes immediately. So, there is some overshoot undershoot, whether it is an ideal buck converter or a practical buck converter, the overshoot and undershoots are there. When there is a step up load transient, there is a voltage undershoot and it is around V0, that means there is a okay. So, delta V0, the voltage undershoot is there, okay, and this is quite large, around 0.5 volt, that means the voltage has reduced from 1 volt to 0.5 volt, which is not acceptable. Okay. So, that means here from this waveform of the converter, we can clearly see that what we talked about, because this converter is you can think of a voltage source, but since it is not regulated in open loop, it has a resistive drop, that means it has a finite DC output impedance, and it also has that AC output impedance which contribute to this overshoot undershoot behavior of the system. Now, this motivates us that if, because it is open loop, we have fixed the duty ratio. So, our one of the objective of the control of this DC-DC converter, the first thing we need to reduce this RD effectively. That means we need to generate the output voltage of the DC-DC converter in such a way, if we draw, let us say the converter is rated for certain current, that means if it is rated for nominal current of 20 ampere. So, if you draw from 10 milliampere or 100 milliampere to 20 ampere, throughout the current range the voltage should be nearly 1 volt, that means almost constant. So, that can be achieved by closed loop control, and we will see soon in the subsequent lecture. We need an integral action to reach steady state error, but that may take some time. The another thing we will see, the need for control is to, this undershoot is not acceptable, because in the very first lecture we told that in processor application where our current repeatedly will change, like a large step transient happen, step up, step down. So, and this voltage will be supplying to a digital processor where such voltage difference can completely lead to a malfunction of the digital circuit, because the digital circuit has certain noise margin, that means it has a certain voltage range for which the logic level will be treated as 1, and if you go beyond that, then the digital circuit will start malfunctioning. So, the DC-DC converter has to be tightly regulated within the noise margin of the DC, that means digital circuit. So, we need to apply some control logic such that the undershoot can be substantially reduced, so that the whole profile of the voltage can be within the limit of the digital circuit for which we are designing the power supply. So, that means it motivates us that we need to do something closed loop control. The few more things we want to highlight, the buck converter operating using ideal and practical voltage source. Then we want to see, okay, so first let us go to the MATLAB, one by one we will check. Okay, here what we are considering, if you go to the Simulink model, you can see this is our DC-DC converter, this block. So, this block is DC-DC converter, and this is our actual voltage, practical voltage source impedance. I will not say source, the impedance of the practical voltage source, impedance of practical voltage source, because ultimately it requires a supply which is here, okay, which is here. Okay. Now, so what is going to the converter is actually output of this practical voltage source, which is nothing but an ideal voltage source followed by its impedance of the supply. Okay. Then the other things are same that we have discussed, that means we have a converter. Here we want to mention, that means we are applying some step transient. This is a resistive load 1 by R that we have also discussed, but along with resistive load we are applying some current step load, and here if we go to the MATLAB Simulink block, in the source you will find, if you go to the library, in the source you will find these step blocks, okay. And if you go inside the step block, it will first term, it will ask for step time, that means at what time you want to apply the step transient, that means you may not want to apply the transient at the very beginning. So, you want to apply this step transient after certain time. So, this is called the step time. If you set it 0, then step will appear at the very beginning, and we are not going to do that. The second thing, it will ask for initial value. So, naturally the initial value is 0 because the step load will appear after the time. Then the final value, how much value you are going to apply, that means what is your step size. Okay. So, for this block I have defined custom, that means the T step I am defining in my .m file, and the step size of load current I am defining from the .m file. Okay. Similarly, for the source also I am defining all these parameters from the .m file, and delta V in, that means how much if I want to make a supply transient. Similarly, I can create a step transient in the reference voltage. Okay. Now, if you go inside this block which I have shown, this block I have already shown. If you go inside, I have implemented this inductor dynamics of the filter, source filter, then the capacitor dynamics of the source impedance, and then this is a converter that we have discussed. Now, what are we going to do? We are going to create a test cases. First thing we want to create, that means we want to run with a practical voltage source first, or let us run with an ideal voltage source. Okay. So, if we apply an ideal voltage source, okay, let us say we are applying an ideal voltage source, that is a fixed value, we are not applying any transient. Okay. So, we can take this same as this ideal voltage source, Now, this converter is running by an ideal voltage source. Okay. So, let us run this simulation. So, in this particular, see, you can see the source voltage I am drawing. So, it is perfectly 12 volt. That means, since it is an ideal voltage source, it is perfectly 12 volt, and you can see the converter inductor current waveform. Okay. So, this is the inductor current waveform which you have seen earlier, and this is the output voltage waveform. We have set a duty ratio 1 by 12. So, there is a drop, and that we know, we have already seen the drop, but we have not investigated fully the reason. That we will investigate in the subsequent lecture. Now, on top of this, that means we can see clean source voltage if it is an ideal voltage source. Now, I want to show the next case study on top of this. That means, now I want to connect here the practical voltage source. That means, here is the practical voltage source, and here I want to show the practical voltage source. Okay. Now, in the case study, I want to repeat overlap this with the waveform. I want to do okay. So, let us run it. Now, this is with a practical voltage source, the same DC-DC converter, same duty ratio, but now with a practical voltage source. Okay. So, let us see what happened. So, if you see here, if you zoom it, a practical voltage source, you see, that means there is a transient effect, because we are putting transient effect. Here 12 volt was the one when there was ideal voltage source was connected to the DC-DC converter. Now, because of switching event of this DC-DC converter, you see the output voltage waveform got changed a little bit, shape has changed because we have overlapped these two waveform. They look somewhat very close, similar. Okay. And if you go to the inductor current waveform, they look very similar, identical. That means, if the impedance of the output source is not, and the effect due to the transient in the source is not very severe, because if you see the magnitude, it is varying from 11.92 to 12.06. So, that means, it is roughly around 60 millivolt, which is not very large quantity, but we can clearly see, because our switching frequency is how much, is 2 microsecond. So, if we extend this, if we go close to this, let us go increase in millisecond. So, you can take from these two waveform 1 millisecond. You can, if you go further, there is a jump, because of ESR of the source RC circuit, and then again if we go here, okay, again if we take up this, so here also you will get one jump. Okay. So, this jump phenomena is because this ESR jump will be direct jump when you suddenly apply a load step and when you suddenly remove. So, here we are not applying any load step, because the buck converter current is discontinuous, and that appears like a load step to the source, and that is why it is responding. Now, what will happen if the impedance of the source converter, that means, suppose I take 2 microhenry, suppose you put a thicker wire, that means a long cable wire, where it introduces sufficiently large inductance 1 microhenry, earlier it was a 2.2 microhenry, and we want to repeat this simulation, and I want to create another color, green color, okay, and see I want to see the effect. What will happen if we, that means I want to see as if the cable impedance, the length is increased and we have some inductive effect. And you can see now there is, the effect is somewhat significant now. It is no longer I would say. So, let me run it once more. Yeah. Okay. So, if you take the effect, it is no longer negligible, because if we take around 1, particularly during the input, like this side, you will see there is also a slow scale oscillation along with the switching event, and that oscillation slowly damping out, because there is a LC circuit and their frequency, resonating frequency, or basically LC frequency, it is damping out, that coming, and that is interfering with this event, and that is why we can see the effect due to the supply variation. So, that means we have to be very careful when we are connecting a power supply for running a buck converter. Our buck converter should be attached very close to the power supply, and if the length of the cable is too long, then that may introduce the inductive effect, and that can create lot of problem trouble in the converter, because it has a switching converter. So, that will introduce the LDIDT will increase, and also the oscillating behavior will come. Okay. So, that means this is one of the very important point. And if we want to see the effect due to the output voltage, as of now output voltage effect is not very significant, they are somewhat similar, but if you keep on increasing this inductance value, then it can be severe. That means the effect can be really severe, and if you see the current waveform, they are not significantly different, but at the same time they are not exactly identical. So, there is some difference. So, that means I have shown you the effect due to this ideal and practical voltage source. Now, understanding this conducted EMI, since the input current is discontinuous and you have some parasitic effect and the source impedance effect in the voltage supply. So, we saw that the voltage of this output voltage is actually affected, and you can see there are high frequency components are present there, because even if you want to take the Fourier series of this particularly corresponding to switching frequency, there are dynamics. So, that means if you take one cycle here, so there is transient effect here. So, this transient effect if you take, because there can be rise time, fall time, we still have not incorporated the switch model, that means the parasitic model of switch. If you include, then it will have some ringing effect, and that is why it will introduce some distortion in the power supply, and that will lead to conducted EMI problem. Okay. Okay. So, conductor EMI. Then we want to see understanding transient response, supply, load and duty step. So, right now what we are doing, we are making a steady state response, there is no transient. Now, I want to see, so with this filter let it be there, I want to see what is the effect due to the transient. So, let me first make this blue color. Blue. Okay. So, now I want to create some transient cases. What do I want to do? I can make a load transient by introducing a 20 ampere load step, and let us see what happened. So, I want to see the load step transient. Okay. Now, this is with a practical voltage source, and you see this is our output voltage, because it is open loop, and we have just discussed that open loop, the steady state point will get shifted because there is a DC drop, and that can be, the DC drop can be visualized by considering as a series resistance, output resistance of the source you can think of. So, DC-DC converter can be treated as a source, where it has a in open loop, it behaves as a finite output impedance DC value. It also have transient effect that we saw in the previous simulation, and there it is also clear here. And if you take the inductor current waveform, then the inductor current waveform also have this transient effect, but you can also see on top of the its switching behavior, there is some small scale oscillation is happening. This oscillation, if you take this oscillation, that means if you zoom this oscillation, is due to this filter oscillation. That means if you go back, so it is getting reflected into the waveform. This oscillation, that means a supply oscillation is getting reflected to the output side through current, and if you take the waveform of the output voltage, if you zoom it, you will see the oscillatory behavior. That means, any oscillatory behavior in the input side is reflected in the output side to some extent along with the DC value, and this particular term is known as audio susceptibility. That means, if the supply voltage has any disturbance in terms of oscillation, whether power supply is able to reject it or it will appear at the power supply end. That is what we are going to audio susceptibility effect, and we can clearly see that this slow scale oscillation on top of switching frequency is coming due to, you can see the slow scale oscillation in the output voltage is due to the supply oscillation. That means, this is something we have to talk about. Okay, so we learn about power supply, we saw about due to a load step, we can talk about duty ratio step, okay, that will give some condition of bandwidth concept, then we can also talk about the supply. Now, we want to see other transient effect just to get, okay, so this load transient we saw. Now, we want to see there is a, if you give a duty ratio change of 0.1, that means you apply a duty ratio 0.1, we want to see what happened if you apply a duty ratio step. That means, we want to increase the output voltage. Again, we are increasing the output voltage, and output voltage was originally here, it was the duty ratio is 1 by 12. Now, with that duty ratio we added 0.1, so it has increased, and you can clearly see the oscillatory behavior, and it is coming because of the oscillatory behavior of the output voltage, that means the source. So, source has this oscillatory behavior, that means you have not connected the cable properly. So, the cable is carrying impedance and your source also is a nice source. That means, when you are talking about DC-DC converter, we should use a good power supply as an input to the DC-DC converter, because if the power supply output impedance is not good enough, then you will get such impact in the converter performance also. Okay. So, we saw that, and the last part that we want to discuss is that if we apply a supply transient, that means we want to apply a supply transient, let us say we apply some -6 and we want to see the effect. So, in this case we have not applied any duty ratio or load transient, it is a supply transient, and say we have applied a supply transient and we have changed the output input voltage from 12 volt to 6 volt, and you can see severe effect at lower input voltage. The effect is very much severe, and it is clear even from the inductor current waveform. That means, there is a, along with the switching behavior, there is a effect due to the input filter source dynamics, and it is coming from because of the source. So, source voltage is fluctuating too much, and that is not acceptable. So, this motivate us, that means we have checked the transient performance. So, if you take ideal, such oscillation will not come. So, we understood this. Now, the startup behavior. The another thing we want to check is the startup behavior. Okay. So, if you want to check the startup behavior, that means we are not applying any transient, okay, but we want to start everything from 0, okay, and we want to, last thing that we want to check is the startup behavior. If you start the power supply, okay, so this is a startup process, and if you see the startup process, the current start from 0 ampere, it is ramping up and it is coming, again it has oscillatory effect due to the input supply that impedance, and output voltage also changing from. So, this is in open loop condition, we are just running the converter in open loop. So, this is very much clear that the process, this startup is giving a huge voltage overshoot, which is not acceptable, okay, and the startup time is also too large in terms of millisecond. You can see it is taking like around 0.15 millisecond, and another point is very important is the current is too much, that means the startup current is also too high. Okay. So, with this we want to now realize that we need some startup behavior, and we can also realize the short circuit open circuit behavior from this, and From there it is very clear that supply disturbance can severely affect the performance of the converter and it can introduce lot of oscillation. So, if you connect many power supply in a single source and if one of the power supply injects such behavior and if your source is not properly it's not properly regulated, then it may propagate to the other converter and it can create severe problem to that connected converter, interconnected converter. So, we need to really, so one of the requirement is need to put an input filter for each converter, but putting each converter a large input filter can cause not only the power density, the size effect, it can also cause the other problems such as the closed loop bandwidth of the converter will be also affected by the input filter, and that we will also discuss in another lecture. Okay. So, that means it require a closed loop control which can, instead of putting too much emphasis on the circuit part which we have to do some minimum amount, we need to stress on the control part, how control can ensure such transient behavior will not be propagated to the output side. Even though input has a disturbance, output should reject it, okay, and it should be also stable so that the filter requirement can be reduced. So, dynamic requirement, now we understood we can take a boost converter. So, that means we will see in subsequent lecture, if there is any change in the duty ratio, it will affect the output voltage and where we can derive a control to output transfer function. If there is change in any load current, it will affect through the output impedance. Okay. So, the converter objective can be divided into static objective, dynamic objective, operating requirement, then fault protection and management. So, the static objective is a steady state, that means we have to make sure what is the voltage ripple, current ripple, what is the DC average value, and this thing we have discussed in previous lecture, and today we want to touch upon briefly how to design the power stage, and we also want to show some web bench design tool from different industry, like as a designer tool. Then dynamic objective, we need to meet certain transient requirement, we need to cut down the overshoot undershoot within a limit, we need to reduce the settling time. Okay. The operating requirement, we need to make a compliance with the conductor EMI, because we saw the source characteristic can drastically affect the converter. So, we need to put an input filter to reduce the EMI. The power of sequence is something, that means if there are multiple converters are connected and if all of them want to go to load transient, then we cannot enable load transient for all the converter because that may collapse the power supply. So, we need to make a sequence of transients such that you can prioritize which one is the critical, so that we can save the power side, the source side. Okay. Similarly, the soft start is required so that we can limit the current, and at the same time within the current limit the startup can, and we can achieve fast startup. Then what swapping we told about, that means we can remove one of the power supply if it is faulty in the network without turning off the whole network. So, that should also be possible, and you can create similar this case study in MATLAB what we have discussed today. The fault protection and management, we need to consider startup circuit, we need to protect the inrush current so that the current should not exceed the tolerance limit of the component. Then meantime reliability is important, we need to keep on checking the component and check the waveform and try to estimate the health condition of the component. Then the thermal protection, because if too much current is carrying and if your impedance has more resistive effect, then it can get heated up, and if you have a more conduction loss or switching loss, then you need to have proper thermal management and heat distribution. Okay. And particularly for present age where we are going more towards GaN and silicon carbide, so packaging and cooling is a very important requirement which should be part of this. The important requirement, steady state requirement, input voltage range is very important. We worst case current ripple, the losses, the device rating, that will decide on, and we will also talk in the loss analysis that range of input voltage is important, particularly for light load efficiency. Then the nominal efficiency, it will decide the switching frequency also. Output voltage value is important to know what is the maximum or the minimum duty ratio that we have to achieve using the converter. Okay. Then what is the acceptable ripple limit, then what is the acceptable undershoot overshoot, though it is the steady state characteristics, we will not talk about overshoot undershoot. Then what is the maximum load current, that will decide how many number of phases. For a single phase converter, generally 20 ampere current is reasonable, but if you go above that, we need to consider more number of phases. Then another important is the modulation technique, which in most of the cases we do not consider, because we by default consider PWM. But in this course we already talked about constant on time, constant off time control, and in subsequent lecture I will show you the worst case scenario can be drastically different under different modulations technique. So, in order to decide the frequency range, input filter design, the ripple characteristics, we should consider also the modulation technique. Now, there are few commercial tools, I am just presenting few of them, like a Texas Instrument Webbench, then ST Microelectronics eDesign Suite, Infineon has its own, then ON Semiconductor, and there are other industry also, they have their own tool. And if you go to that tool and if you give your input output voltage, load current specification, it will create a bill of material, so that you can even know the parts of the inductor, capacitor. It will be helpful in the power stage design also. Okay, but you can have your own controller. Then if you take an example of a buck converter for 8 to 15 volt with a nominal 12 volt input, and we want to achieve 1 volt output with 2% ripple, the maximum load current is 20 ampere, and the modulation technique we can use the PWM or a combination of thing, because we will discuss this in the light load control technique. So, in the inductor design, we know under PWM the worst case ripple that we have discussed, that will happen at the highest input voltage. So, if we keep 20% ripple criteria of the maximum load current, so ripple is set to 4 ampere, and we should calculate this ripple at the highest input voltage, because there will be the ripple will be worst. Then that will give us the duty ratio range, and at that duty ratio the nominal switching frequency, if we create 500 kilohertz if we take, then our minimum inductor value should be 467 nanohenry, and in our simulation we took 0.5 or 500 nanohenry or 0.5 microhenry. Similarly, if you take the output voltage ripple, we can calculate the output voltage ripple at the highest input voltage, that will be the worst case, and then if we consider 2% of the nominal ripple, then it is 20 millivolt, and that should be calculated at the worst case, and this will give us the minimum output capacitance to be 117 microfarad. So, in our simulation we took 200 microfarad. So, we choose these two for our subsequent lecture in our future lectures. Then understanding operating requirement, we discuss about electromagnetic interference effect, the power of sequencing, that means multiple converter, if it undergoes transient, then we need to create a sequence of event, and now power management bus actually is coming up, and which can be used for digitally controlled converter to communicate between multiple subsystem, because we talked about multiple POL for a smartphone, where each POL will undergo different transient while driving its load, and but the battery is a single source. So, we cannot accommodate all transient event to happen at the same time, then the battery will collapse. So, then we have to create a sequence of transient, so that we can reduce the burden of the battery, and that is also important. Then what plugin is also important, so that if you go to data center, there are racks and your rack power supply. If you want to take out one of the faulty unit, then the whole system should not be stopped, that means it should be in the running condition, we can replace the unit. So, those features are important. In the fault management, we need to put an inductor current limit, inrush current is important, thermal protection is also important, packaging and cooling requirement is very important, and we need to check the health monitoring. Then overall thing, it turns out to be that control will play a significant role, because we can take the control technique, using that we can actually incorporate the startup behavior, we can shape the startup behavior, we can shape the inrush current, we can protect. If there is a fault, by means of a current limit, we can save, we can disconnect the power supply. Similarly, we saw about the effect of source variation in the output, that can be rejected completely by means of control, okay, by means of feed forward or even feedback, or a combination of feedback and feed forward, that we will see in the subsequent lecture. Similarly, by means of modulation or by means of control, we can do active EMI reduction by means of frequency modulation. So, all this can be incorporated into the control. So, control can play a significant role in order to improve performance, in order to achieve close to zero output impedance, in order to achieve the fault protection, I think fault tolerant power converter. So, all this can actually enable this feedback and feed forward control can play a significant role. So, in the rest of this lecture we are going to take, now we are somewhat very clear the need for the control. Okay. So, in summary, the impedance aspect of a practical voltage source was discussed, the scalable and plug and play MATLAB model development, that process, that also we have discussed. Then we also discussed MATLAB case studies to demonstrate control requirement, and we also discuss briefly the power stage design guideline and few power designer tool. So, with this I will finish here. Thank you very much.